All right, so thanks for making it all the way to the last talk. I know some of you guys had apparently a pretty rough night making it back, so in any case, I'm not sure what I told you at the beginning I'd be talking about for the tutorials, but I'm going to talk about something different that I thought would be kind of fun as a way to think about how a very natural information theoretic type question becomes quite different when you talk about it in a learning context where you don't get to choose, and nature gets to choose the types of things you're trying to recover. So I'm going to tell you about a different random walk through learning. I'm going to tell you about something called population recovery. So Anoop knows a lot about this, but in any case, let me borrow a story that I think originally comes from either Avi Vigderson or Amir Yehudayev to introduce this problem. So it's a kind of fun way to think about it. So imagine, we're all math, information theorists, what have you, but some of you guys have hobbies. What if some of you guys moonlight as paleontologists on the weekends, and you enjoy digging up dinosaur bones, but the trouble is that each one of your dig sites, you never really get a full entire dinosaur skeleton. Instead, what you get is just a collection of a few different fragments of it. You might get a hand here, head, jawbone here, and a collarbone somewhere else, but you don't get the rest of it. Now the question is, across all of these different dig sites, the species which the skeletons came from were different, right? So the question is, how can you actually stitch together these very partial snapshots of what's going on in a population together to get a complete view of what that population is? So let me tell you one way to try and turn this into a mathematical problem. And it's going to sound a little bit like the deletion channel, but there's some really important differences to what's going on here that I think is a great way to think about this issue that's come up again and again about, in coding theory, you get to choose the types of things you're passing through a channel, whereas in learning, nature chooses for you and you don't get such a choice. But the basic idea for population recovery is, can you reconstruct some description of the population from just these fragments and stitch them together? So the way that I'm going to formalize this is there'll be k different types of species of dinosaurs that roamed the Earth eons ago, and there are n different features associated with each different species. You can think about these as binary features. Do they have this type of jawbone or this one or what have you? But in any case, what's going on is that each one of these species is described by some binary string of length n that tells you which features it does and doesn't have. And of course, this isn't quite a full description of the population, because what's also important is some notion of these underlying probabilities associated with each of the different species. So among all the dinosaurs, what fraction were each of these different species? So this is your underlying ground truth that you'd like to be able to recover. Now, what's your model for how you actually get information about this? Now, the problem is that when you actually dig at a dig site, you're going to get a very partial and obfuscated view of this string. And what's going to happen is you choose one of these species with probability proportional to pi. And whatever that string is, we can imagine maybe you delete some large fraction of the coordinates randomly. And what will be important for this talk, so you actually know when something is deleted. So you see a question mark there instead of a 0 or 1. But in some places you don't see a question mark and you really do observe the feature. And to make this problem a little bit stylized and easier to think about, you think about these as independent deletions. So the interesting thing is, what happens if you end up deleting 99% of the coordinates randomly? See, the issue is that for a typical sample, it very likely could be the case that even if you knew the full description of the population, the thing that you wanted in the first place, you might never be able to know which of the species it was. So much of it could be obfuscated that you actually can't figure out which dig site was which species, but nevertheless, even without ever being able to figure that out information theoretically, you'd like to be able to stitch together these partial observations that are almost entirely obliterated and figure out what was going on underneath. Sorry, erasure, my mistake. Good, thank you. You can think of it as being related to an erasure channel, not a deletion, my mistake. But of course, here the issue is that we don't get to choose what these underlying strings are. If we did, we might be able to choose strings that are in some code book of some good code for the erasure channel, and we would be able to recover which string it originally came from. But the issue is that you really could have pairs of species that are quite close in Hamming distance. If, for example, they were close to each other on some sort of evolutionary trajectory, they might not differ in that many locations. So that would be an issue because that pair would be very likely to be confusable with each other. So this model was introduced by Zev Dvir, Anup Rao, Avi Vigderson, Amir Yehudayev. I'll tell you another motivation for it later on, which, not just from paleontology, but this is called lossy population recovery. So just to make sure we're on the same page, this is the notation I'll be using throughout. So there are k different species, which are binary strings, A1 through AK. They have underlying probabilities P1 to PK. And the issue is that, there's some mu, so that when you choose one of these underlying strings, each coordinate is deleted independently with probability 1 minus mu. So think of mu as being something incredibly tiny, like 0.01, so that you're deleting 99% of the string. And the basic question is there a polynomial time algorithm for actually recovering the underlying population? In fact, it's not even clear that there's an information theoretic bound that you can actually solve this problem to begin with. And it's an interesting example of how sometimes in learning, the heart of actually the algorithmic challenge is actually proving an information theoretic bound. I think that's really all there is in this problem, is that once you have an information theoretic bound, it's very directly to translate to an algorithm. So I'll tell you about some interesting tools for actually proving that this problem is actually solvable. There's a harder problem that I don't know how to solve, which is noisy population recovery. So this was studied later by Vigderson and Yehudayev. Even more natural, because you have unknown k strings, probabilities P1 to PK. But now the catch is that you don't know what's been changed. So instead, you're going to have some flip probability with half minus eta. Now, you want to say that even for very small values of eta, like 0.01, where you're getting very little signal, that you really can recover the underlying population. And of course, if you could solve this problem, you could certainly do lossy, because every time you see a question mark, then you just flip a coin, put in a random 0 or 1, and it's the standard relationship between BSC and BEC about how some reasonable code for one gives you a good code for the other. And let me tell you what's known about this problem. So it's kind of funny that it turns out the problem is trivial for reasons that are not at all obvious when mu is at least a half. When you keep at least as half as much information as you delete, but it's really non-trivial to get below a half. So in the first paper they showed it down to 0.36. And then Vigderson and Yehudayev showed a quasi-polynomial time algorithm for not just lossy, but even noisy, using very different techniques. We're actually going to be following the framework of the first paper instead, but I'll show you some cool tools for actually doing it. In fact, Vigderson and Yehudayev showed that their technique actually provably can't yield a polynomial time algorithm because they actually showed lower bounds against their style of arguments. Batman et al., it's always good to be improving upon Batman, showed that there actually is a polynomial time algorithm for any mu at least 0.3, and they actually conjectured that it wouldn't work beneath 0.25 for kind of interesting reasons that I can conjecture about later. But it turns out there's actually a polynomial time algorithm for any mu greater than 0. That's what I'm going to be telling you about. And this will be a kind of fun story because this will be a weird proof, but I like it. So let me tell you about perhaps what's the real motivation for studying population recovery, dinosaurs aside. So there are important circuit family, types of formulas in CS. One of the most popular things is DNF. So here, disjunctive normal form, you have variables, and they either appear directly or they're negation. So I'll put a bar on top if it's their negation. And how this formula is evaluated is it's just an OR of ands. So each thing checks for some particular configuration, and then you output the OR of whether any of those configurations are entirely satisfied. Now, in fact, this is this is a very standard question to study in learning, that it's a very natural model of some of the labelings that you would see. So in supervised learning context, when you see some example along with some categorization of it, a lot of times you assume that underneath it is some DNF formula that actually tells you what the label is. So the issue is, if you were actually given some distribution D that generated examples, and you'd see the full configuration of what the settings of the variables are, and then you see the evaluation of what the DNF formula is, can you actually learn a DNF that approximates the original one according to, say, the distribution D? So this is in Valiant's famous pack learning model. So all you see is the actual configuration of values for the variables along with a black box evaluation of the DNF formula, whether it evaluates the 0 or 1. So the issue is that in standard learning types of problems, especially in supervised learning, we are shockingly stuck. So if you ask this basic question, what is the best algorithm we know, then we know something quite interesting because it's way better than 2 to the n, but it's 2 to the n to the 1/3, and it comes from some strange Chebyshev polynomial tricks, and that's the best that we've known for about 15 years. And in fact, even if you restrict the simple distributions, there's actually something trivial that's pretty good. So imagine D is not just any distribution, as is standard in pack learning, but it's the uniform distribution. So you choose a uniformly random assignment from the Boolean hypercube. Then what I claim is that there's a much better algorithm, because any clause in this that's too long, imagine it's 100 log n long, it just has no chance of being satisfied. Its chance of being satisfied is 1 over n to the 100. So you just throw away all clauses that are too long and forget about getting them right. And the remaining ones, you could just brute force search over and keep pruning them down as you know that they're not actually in the formula. That gives you a quasi-polynomial time algorithm that is so easy I don't even know who to attribute it to, but it hasn't been improved upon ever in the uniform distribution. So, their idea, Viridal's idea, was to try and change the problem slightly. So instead of,
So how do you learn it if you have a large clause that has 100 log n terms? You drop them out.
You drop them out, because in pack learning, your goal is to learn a DNF formula that's close to, pack stands for probably approximately correct. So you're allowed some probability of failure. That's fine, because that'll be over the random draws. And the approximately corresponds to the fact that I can drop the large clauses, which don't usually get triggered, so that's fine. That's the idea. In any case, so one way to try and make progress on this is to try and change the question. So imagine instead of black box access to the formula, you got a little bit more information, something leaked about what actually was going on in the formula to get you that value. So here's one way to try and interpolate between these two, is to give some type of gray box access. The idea is that what if not all of the bits are set? So instead of randomly setting every bit, what if you only set 99% of the bits? And the remaining 1% of the bits remained live. So what's going to happen is when you set a bit, you can actually do something to the formula. If I had a formula and x1 was set to false, then I could just prune the first clause because it is never going to get turned on. So what I would see at the end of the day is some sort of pruned formula. But the issue is that this pruned formula, things that survive, are partial snapshots of the clause that generated them. So it's very naturally a population recovery problem where the species are the different clauses. And the issue is that when you see some partial evaluation of the clause, in fact, you're seeing some sort of trimmed down version of what that species is, and you want to stitch them together to figure out what the clauses were. So it turns out that each clause that survives, it's a fragment of its variables. And you can make this precise. It's not difficult. That if you can solve population recovery, you very directly get an algorithm for learning DNF formulas in restriction access. So what I'm telling you is that in the DNF learning problem, over the uniform distribution, there's been no improvement beyond quasi-polynomial. But in fact, as long as you survive at least 1% of the variables, then you can actually get this all the way down to polynomial time. So that's an immediate corollary.
So in the model, you set each bit independently with some probability, and the remaining bits you can play with, or you don't in this.
Oh, so they stay live. So for example, what I mean is imagine, so if x1 is false, the clause dies and you never see it. But if x1 is true, then it gets removed from the clause because it's turned on. And then let's say x3 is true, then that would survive and be removed. And all you would see is the single thing x5 bar, if x5 were the 1% of variables that were chosen to not be set.
It would just be revealed. Okay, I see what you mean. Yeah. So that would be the thing that's revealed to you, and the other ones.
Exactly, exactly. So it's some sort of gray box access into the internal workings of the circuit. Instead of literally seeing the input-output functionality, you get a bit more. But oftentimes you might just see false. So you would actually get no information about the clause, but that's all right. So even if you get nothing, that's okay, because you can take enough samples that you see enough things going on randomly. Okay, so the simple corollary of this is that there's a polynomial time algorithm for learning DNFs, now polynomial, not quasi-polynomial, for any mu, as long as 1% of the variables survive. All right, so this is a kind of fun one because this is going to involve some weird things. So this is about inverse problems because it's about solving this population recovery problem given random samples, where I claim it's not at all obvious that information theoretically should be solvable at all. That was the heart of the issue. But it's also about complex analysis. So what I mean by inverse problems is that what's going to happen, and this is just the foreshadowing, you shouldn't see this immediately, but what's underneath it is that there's some matrix A, and what we really have is we have some linear system AX equals B, where we get some noisy approximation of the right-hand side. Now, it's a very standard problem to then understand how well you can approximate X. That's an entirely basic question that's studied in numerical linear algebra, and the answer is pretty well understood. It's the condition number. But what I'm going to tell you is that actually the A that we're interested in is horribly conditioned. It has an exponentially bad condition number as soon as you delete more than half of the information. But nevertheless, we're not going to be interested in all of X, just one of its coordinates. So it's about how to solve inverse problems even when they are exponentially ill-conditioned if you're interested in just part of it. So that's what the talk is really about, is even though the condition number of A is exponentially large, we're going to find ways around it through complex analysis, and I'll be a little bit mysterious. Let me show you the proof. This is the proof. That'll be the proof, but I'm not going to tell you yet why that's a proof of anything. So let me try and work towards how this is a linear inverse problem and why this is badly conditioned. So let's just try and wrap our heads around what this problem is. So it turns out that there's a challenge problem that really captures the heart of the issue. Population recovery, the way I phrased it, was about given random samples where you can't really figure out which species generated it usually, what the description of the population is. Well, there's an even simpler question. What if one of the species in there is the all zero string? You just want to find out what its underlying probability is. That's an even more basic question because I'm telling you the rest of the species are just noise and you don't care about them. And all you want to do is find what the probability of this one string is, given that there are many other things that can pretend to be the same thing. It's not obvious, but this turns out to be equivalent to population recovery, that if you could solve this problem, you could actually solve the entire thing. The idea, I'm not really going to go into it, but the quick sketch of the idea is that it turns out you can always assume you know the underlying strings, because what you would do is you build up an algorithm based on studying prefixes of the problem. When you look at just the first bit, there are only two strings, 0 and 1. Many species get collapsed into the same one of those two things. You learn their probabilities if you can, and then when you grow out to the second one, you double. Now the point is that you don't keep doubling all the way, because whenever you double and get a string which really isn't present, you're going to be able to prune that out because you learned its probabilities and you never grow too much. And then once you know the strings, there's a way to actually map whichever string you care about to the all zero string. So it's a clever reduction, but I'm not going to go into it. But let's take for granted that this subproblem is the heart of the issue. And let's try and see why this is an inverse problem with a really horrible condition number. So how is this AX equals B? So let's imagine that we have the following setup. We have A times some vector Q. Q0 is the probability of the all zero string. That's what we want. We only want one coordinate of this vector. Q1 is actually going to be the total probability of all strings with exactly 1, 1. So I'm actually going to ignore which coordinates go where and still be able to solve this problem. So this is the total sum of all the PIs where, AI has exactly 1, 1. And similarly for all the others. Now the point is that this matrix represents the transition probability of the probability that the string you started off with before you obliterated things had I1s to begin with, and then ended up with only J1s, and the rest are zeros and question marks. So what that literally is the binomial coefficient, because you only care about what happens on the ones. So you have, I choose J, which J things survive. You have mu to the J, because that's 0.1 to the J, the chance that those things survive. And then 0.99 to the I minus J in the hopes that everything else gets deleted. So this is literally just this very simple matrix whose entries are binomial coefficients. And I want to find Q0. That's the problem. Now, the right-hand side is exactly what you think it is. B0, by the way I've constructed it, is the probability that the output has only zeros and question marks, no ones, because that's literally what this matrix vector product gives us. So it's the probability we get a string that looks like this. Now, B1 is the probability that we see only 1, 1, and the rest are zeros and question marks. So we get a string like this. Now, the issue is that we don't actually know the right-hand side exactly. We're only given random sample access to it, right? If we knew B exactly, the game would be over, because A is actually an upper triangular matrix. You can't create more ones than you started off with. So it's upper triangular, it's certainly invertible. If I knew B, the game would be over, and I would take A inverse and find, Q perfectly, and I would be done. But the issue is that A is upper triangular, and it's exponentially ill-conditioned. In fact, it has exponentially small values along the diagonal, because the entry along the diagonal is the probability that you start off with I1s, and you end up with exactly I1s as the output. You don't delete any of them. So this is something which actually, if you take A inverse, you're going to have a bad time, because all you can hope to do is approximate the right-hand side within 1 over your sample complexity. That's the rate at which you're converging to those values. So really in numerical linear algebra, if you have a bad condition number, you can't do anything. But here the game is that we only care about one coordinate. So if the condition number is exponentially large, but we only care about one coordinate, it's not clear whether you can actually solve this problem or not. So the condition number of A is exponentially large, but let me tell you the strategy that De Vere et al. Used, which we're going to build on. So there's this notion of a robust local inverse, which I think the first time I saw one of the authors speak about it, it didn't sit right with me, because I didn't see why it should be different than things that we knew. But it really is an interesting idea. So let's try and formulate it a different way. So we had that one way on the previous slide where the naive strategy was just to approximate B on the right-hand side and take A inverse and multiply it. Well, if we only care about one coordinate, let's take the vector E0, which is just a vector with a 1 in the first coordinate and zeros everywhere else. And now if I left multiply, that times A inverse, I get some vector X. Now what I claim is that when I take X times B, well, it's, X is literally E0 times A inverse, and B is literally A times Q. So the A's annihilate, and I get exactly the inner product between E0 and Q, which just pulls out the first coordinate. This is just the same strategy said in a different way, but another way to say what goes wrong is that if X has, but it turns out X has exponentially large norm as soon as you delete more than half of the coordinates. So, X is unique because A is invertible. There's one and only one X, which gives us a linear estimator that's unbiased. So what I'm really saying is that if you have an unbiased linear estimator, there's only one thing, and it has exponentially large variance as soon as you delete more than half of the coordinates, and that's just a fact. So as soon as you go beneath a half, it means that you're actually very carefully adding bias, but being able to drastically reduce the variance of this estimator. So the idea is to add a perturbation vector eta, which who knows what this eta is, but what if there's some magical eta so that instead I could add this tiny perturbation to E0, in a way that it moved it off of all of the tiny singular values of A, so that now x bar, which is E0 plus eta times A inverse, is now small in norm and doesn't have too large a variance. While then x bar times B, you can see, again, the A's annihilate. You're getting Q0, but you have some bias on your estimator that corresponds to how large this perturbation is. So the game is there a small perturbation that I can add which reduces the variance from exponential to polynomial? And that's the entire game. So can we perturb E0 so that this resulting thing has bounded norm? Now this is what's funny about robust local inverse. Now I can tell you about where our ideas come in, is that who knows what this eta should look like? You can try and hand design it, but it's kind of bizarre to try and do this because it really looks kind of messy. So the idea is to actually do something different. So I'll tell you, all of the theorems first about population recovery, at least the ones for Lossy early on, are really about building better robust local inverses. So the statement that you can solve population recovery for mu at least 0.36 is just the statement that there is a way to do a magical perturbation as soon as mu is at least 0.36, that there is a way to do it for at least 0.3, and they conjectured it doesn't work, that there was no robust local inverse for mu less than a quarter. And I'm going to show you that there is. And the issue is that we don't really know what this robust local inverse looks like. In fact, even after we prove this theorem, I still have no idea what it looks like. But there's going to be a hack to get around it, which is instead of me trying to construct it, I'm going to formulate it as a linear program where an adversary is trying to prove that there isn't one, and I'm going to prove that the adversary can't prove me wrong. And that's enough. So that's the sort of indirect way of dealing with this issue that this eta vector might look messy, is just to try and dualize to a problem that I'm in control and I just get to prove you can't prove me wrong. So if we take this idea of a robust local inverse and what we want, here's one way. There are many equivalent ways to formulate it that are polynomially related. But one way is that I want whatever this linear function is. So I want x times a to be close to E0. So I want x to be somewhat close to being E0 times a inverse. And x times a minus E0, that represents the bias in my estimator. So I want that in each coordinate the bias is small. It's at most epsilon. You could even make this at most epsilon over n, but this is not a big deal in this. But you also want that this estimator, you don't just want to plug in x's E0 times a inverse because that x would just have too large a variance. So instead you want that this linear estimator is somewhat insensitive. So you want that, let's say its max value is at most some quantity c, which that c is going to govern what our sample complexity is. What are the variance the estimator is tells us how many samples we need to take to get a good faithful approximation. And the first part tells us that it's at least pretty close to the right answer in terms of its bias. So the issue is that this LP, you can solve it on small instances, and you can say, what does it find? But it finds something really messy, and what you're asking is it actually feasible? For what values of c is this actually feasible? So do you need can a polynomial relationship between epsilon and c work? Or do you actually need an exponential relationship between them? It's a question about when is this LP and when isn't it feasible? So the idea is actually a kind of hack, is that instead of actually working with the x's, you can actually design a basis of estimators. One natural x that does not work is to take a value alpha and look at 1 alpha alpha squared and so on. That's called the moment curve. It does not work as an estimator. But if you take many of these moment curves, you could express any x as some linear combination of them. So if you actually instead write this question in this basis, it turns out that it actually makes the LP easier to interpret. So this basis is good for population recovery because it sort of turns it into a problem about polynomials. If you had some linear combinations, a fixed linear combination of these vectors, then that would really correspond to looking at things. If you took an inner product of a vector with one of these things, it looks like evaluating a polynomial at the point alpha. So I won't get into that, but what I will tell you is that what you do get out of this is the following linear program, and this is what I'll prove, is that it gives you, when you take the dual to, this question of is there a good robust local inverse, you get a question about whether a certain polynomial exists or not. So if we can show a certain relation about polynomials, that'll imply that the dual doesn't have a good solution and that the primal does, and that there is a robust local inverse. So this is really the question that I want to focus on, is this, if you believe me, this is what comes out of duality, is you're asking for the question, the dual LP, the guy who's trying to prove you wrong, is asking to construct a polynomial P that has the property that when you evaluate it at 0, that's actually pretty large compared to, epsilon times the L1 sum of its coefficients plus C times the L1 sum of some other polynomial's coefficients, where Q and P are related. So remember, mu comes up in this problem, which is this question about, mu is like 0.01 and it represents how much you're actually preserving about the underlying coordinates. Well, the epsilon and the C were actually constraints in our LP, so they end up showing up in this polynomial problem. But what I'm really going to do is I'm going to show you that such an uncertainty principle holds, that this inequality is never true. That for all polynomials, that actually epsilon times its coefficient norm plus C times some other related polynomial's coefficient norm is large compared to the value at 0. So why I'm calling this an uncertainty principle is that P and Q are two interrelated polynomials. One is just a change of variables from the other. So this is very standard in like signal processing types of things that maybe you guys are more familiar with. If you think about, some signal in one basis, and then you take its Fourier transform, you have uncertainty principles that it can't be sparse in both of them. So what I'm really asking is, if you take a polynomial that's not 0, because it has a large value at 0, so it must be actually a polynomial and not something trivial, can you actually prove a lower bound that the values of its coefficients can't be both small in two different related linear transformations? But the issue is that in something like signal processing, you get to choose what those two different representations are. You choose one basis, the standard basis, and the Fourier basis, which are basically as uncorrelated as you could hope for. But here in the learning problem, as mu gets smaller and smaller, you're obliterating more and more information. So the two views of the problem that you want your polynomial not to be able to hide into become closer and closer. So the question is there still an uncertainty principle that you can't hide? And this is sort of the nature of the information theoretic question going on underneath, but this is really what I want to focus on. So I want to focus on this question. For a polynomial, are its coefficients large in at least one of the two representations? And this I'm going to prove for you. So let me tell you a story about how you get to this. So, if you take a polynomial and you try and understand what its coefficients are, that's very difficult, right? Looking at just drawing the polynomial out on the real line is a little bit tricky, to figure out how that relates to what coefficients there are. But one way to try and get a handle on the coefficients is just understand what the polynomial looks like. So in fact, one way is to try and work with something weaker. So instead of trying to prove that, stronger. So instead of trying to prove a lower bound on the coefficients of some polynomial, that they're not, all negligible, you could instead work with something that's a little bit easier to sort of pictorially view. So what I claim is that if you take any polynomial and you look at its coefficient norms, you look at the L1 sum of its coefficients, I claim that that's lower bounded by the max value of the polynomial in the interval -1 to 1. And this is pretty easy, right? Because whatever value of x I plug in that's in -1 to 1, well, I'm just using triangle inequality. The magnitude of p of x is, upper bounded via triangle inequality, and each of these x of the i's at most 1. So I get, lo and behold, I get the coefficient norm. So if you take any polynomial and draw it on the real line, in the interval -1 to 1, whatever its max value is a lower bound that it has some non-negligible coefficient. So we can ask a new question, which is we can say if a polynomial is large at 0, does that imply some lower bound on its max value in the interval -1 to 1, or this related polynomial q's max value in -1 to 1? So that would be a stronger uncertainty principle, but this turns out to be false. So what would this question mean? So for all polynomials with, which evaluate to 1 at the origin, you could ask whether this inequality is true. So let's picture what this polynomial might look like. So it's 1 at the origin. Now the first constraint really means that you should think about p of x as being at most 1 over epsilon on the interval -1 to 1. Because otherwise it's large just because of that value already, and the inequality is definitely true. So the polynomial is at most 1 over epsilon here. And the polynomial, by virtue of the second part, is at most 1 over c on this interval 1 minus 2 mu to 1. Because I plug in all values of x between -1 and 1, and that's just ranging over some different space. So it has to be really tiny here. So the question is, can you find a polynomial that's 1 at the origin, is really tiny in some small interval around, outside of 0, and is not too large on the entire interval? So any ideas? So it turns out you can, because if I took something like 1 minus x squared to the n over 2, well, it's definitely 1 at the origin, right? I plug in 0 and I get 1. But the issue is that as soon as you go away from the origin, it exponentially damps, right? So it actually hides really, really well. If you chose any small interval, like 0.98 to 1 here, it would just be incredibly, incredibly tiny, off the charts tiny. That's bad. So we can ask, does p of x refute this original conjecture about these coefficients? So the point is, this polynomial, I'm worried that it's 1 at the origin, but maybe it hides in terms of its coefficients all being small. So is its coefficient norm too small? And I claim that it's not. It's actually very, very large, because what I can do is I can plug in a complex value. If I plug in x equals I, well, then I get 2 to the n over 2, and that's that's gigantic, right? So in fact, what I claim is there's a stronger relaxation that even though this problem we defined, this linear inverse problem, which we wrote an LP for, and then I didn't show you how exactly you write down that LP, but you get it into this polynomial question. Started off with a question purely over the reals, but for some reason, understanding the coefficients of a polynomial becomes easier to do in the complex plane than over the reals. Because you have polynomials like this one that have very large coefficients that can hide along the real line, but they can't hide from us along the complex plane. They have to escape and become large somewhere. So the idea is that the same proof we gave that the coefficient norm is lower bounded by the max value of the polynomial in the interval -1 to 1 applies immediately when you restrict to the complex unit disk too. It's the same exact proof, it's just triangle inequality. It's still modulus at most 1. So this gives us a revised question to try and make headway that was motivated by this one counterexample to our original thing. Is it true that for any polynomial, its value at the origin is gives a lower bound for its max value? That I'll translate what this means the same way. So what this really means is that if we had a violation of this type of inequality, the first part would mean that the polynomial is at most 1 over epsilon, not just in the interval -1 to 1, but on the unit complex disk. And the second part would say that p of x is at most 1 over c, not just on the interval 1 minus 2 mu to 1, like before, but on a smaller disk. On a disk centered at mu, on 1 minus mu of radius mu. So that's the mechanism by which as mu gets smaller and smaller, the radius of that disk is shrinking and shrinking. So the region where the polynomial needs to hide becomes tinier and tinier because you're deleting more and more of the information. So it's a kind of interesting way to see how it translates into geometry. But the question is there a polynomial that can be 1 at the origin, that can be not too large anywhere inside this larger disk, and is extremely tiny, on this much smaller disk? And there is no such polynomial. Let me tell you why. So there's this beautiful, there's this analogy in complex analysis between understanding properties of holomorphic functions and random walks. So the point is that if we have, any nice function in the complex plane, there's a beautiful result called the Hadamard three-circle theorem that if we take any nice function in the complex plane and we look at its max value on 3 concentric disks, so one disk, the second disk, the third disk, well, that actually the value in the middle disk is geometrically bounded by the max values on the inner and outer disks. So what that really means is conceptually is that if you have a function that's nice and it's really tiny in this inner disk, but then it grows to something reasonable, it has to continue growing. So it can't just abruptly stop. So it can't start to grow really fast and then plateau out and then continue at that same level. So I won't really give you that much intuition behind that, but I can tell you more offline. But this is the statement, is that it depends on the radii, but if you think about the radii as being constant, then you have a linear relation between the max values that depends on the ratio of the radii, and that tells you the statement that actually the max value in the middle disk can be geometrically bounded by the max. Yep?
Excuse me, so you said that it is hold for all the functions?
All holomorphic functions.
Holomorphic,
yes.
Not only for polynomials.
Yes. That's very important.
They are irrelevant then, polynomials. I mean, you need it for polynomials, but actually it's...
Yeah, so in fact, if I only, let me answer that slightly and then tell you more. But if I had the statement only for polynomials, I would not be done because of an issue that I'm about to describe. So I really do need this for holomorphic functions and not just for polynomials. But actually, there's another piece of intuition that I can, add, right? So, what happened with this weird counterexample where we had this thing which, was 1 at the origin and hid along the real line? Now, the point is that in complex analysis, one of the most basic things is that if you take some nice function, you take its value at a point, if you integrate around a disk around it in the complex plane, you get back the original value, exactly. But there's a nice analogy in complex analysis between these types of statements and random walks. What they're really saying actually takes you back to the heat equation, that it really says that if you take some point in a nice function, that you can actually figure out its value by instead taking a Brownian motion around it and looking at the average value of the Brownian motion in some hitting part. And that's how you can recover back the original thing. So that turns out to be true. That's one of the reasons why, if you had the value 1, you couldn't, at the origin, you couldn't expect to be exponentially small everywhere in the disk. You need more powerful tools like things like this. But why I'm not done, so what this really tells us is, this nice geometric bound. Now, I already told you actually the proof by pictures. The idea is we want to say, now a related thing, that if we have a polynomial that's really, really tiny here, we get to drive C, 1 over C down, because that's just increasing the variance of our estimator. But we want to say that if we choose C to be polynomially large and can drive this really down, that if the polynomial is tiny here and reaches 1 here, that it actually has to become exponentially large, and it can't remain bounded on the outer disk. And the idea is to actually just draw another disk, right?
The max are taking from the boundary or
On the boundary.
so you're throwing away the information about the
Yes. Yeah, exactly. So here, this one, I will be taking the max on the boundary. This guy, you can even take the max inside. But in any case, the idea is just to literally draw another circle that now passes through your origin. So we know that in this middle thing, that the max value has to be large because it hits 1 at the origin. Now the idea is you want to map between these two things. The Hadamard 3-circle theorem tells you some growth properties that can't happen, and we care about another growth property not happening. So this is the Hadamard 3-circle theorem. This is what we want for population recovery. And you can actually use something called the Mobius transform. So if you ask, so that was the point, was that there are nice maps that you can apply that preserve the fact that you're holomorphic and actually map the complex disk to the complex disk. And that family of things that exist is fully characterized, and it's described by the Mobius transform. So it turns out that there is a Mobius transform, which all Mobius transforms map the outer disk to the outer disk. What I really need is that I choose this middle disk, and that what it gets mapped to passes through the origin. So it doesn't actually have to look like a circle. That's fine. And then what I want is that inner disk, it doesn't get mapped to a circle, but it gets mapped inside the circle that I care about. Because in my original setting, I have that the polynomial vanishes everywhere inside. So then I know that growth property can just not be achieved through this. So it's kind of a bizarre thing. This is a little weird, and I don't have any other intuitions for you besides this. It seems a bit mysterious to me that you have a learning problem, which sounds like a natural coding problem that's easy to understand, like the binary erasure channel, but it's very different for learning. Even the information theoretic statement's not obvious. And somehow we wrote an LP to take the dual to use complex analysis to prove that you could solve the learning problem works. So I thought it's a cool outline of, yep.
But is it that Mobius Transform complicated? Can you show us?
The Mobius Transform, so it's just the ratio of two linear functions. So, it's parametrized by like, SL2Z, and if I wrote it up, I would get the wrong signs, but it's just the ratio of two linear functions, and has the property that the complex disk goes to the complex disk. So it's the starting point of things like the Riemann mapping theorem. But then understanding what the inner disks go to is something that you can just write out easily. And the nice thing is it's the full characterization. So this to me strikes me as really bizarre. So I thought I'd offer, it's fun to not only have talks that look like we understand everything, but this I don't understand. I mean, I guess I can follow the details of the proof, but it still looks weird to me. Is that the way to solve population recovery is to prove an uncertainty principle about polynomials through complex analysis, that if they're large at the origin, if they're 1 at the origin, that they can't hide in two somewhat related different bases. And those bases get closer and closer as the problem gets harder and harder. And yet that in turn implies that the LP is feasible, the one that was looking for a robust local inverse, because we got this uncertainty principle by taking the dual and asking someone to prove us wrong. That implies a robust local inverse exists, and that through these de Vere et al. Reductions gives us an algorithm for population recovery. So, those are the main theorems. That's how you actually can learn DNF formulas and restriction access model. Bizarre. But many open questions, so I don't understand any of these things. Why should you be able to solve inverse problems when the condition number is exponentially bad? I have no idea. It seems pretty mysterious to me that there are magical ways to perturb the plug-in estimator that add bias and drastically reduce the variance, that you can do things that you could not do with an unbiased estimator. You really cannot do this with an unbiased estimator. I don't understand how much further that would go. There are other examples within theoretical computer science of where non-plug-in estimators can actually do very interesting things. Like there are things called approximate inclusion-exclusion, where you really do need careful perturbations, and you write an LP to try and find the inverse formula. There are also some of the valiant estimators for entropy, which are non-plug-in, and do things that plug-in estimators cannot do. Robust local inverses seem pretty cool. I don't know where else they could be used. And I guess the main technical thing is, can you actually solve noisy population recovery? Because all of these things fail when you talk about noisy. So I think I'm going to end there, and I'll take any questions you guys have, but thanks for your attention.
So I have a stupid question. So I cannot understand. So you have 3 disks which have a common point. But how can you convert them to 3 disks which have no common point? So
right.
What do you do?
So the statement is that you start off with 3 concentric disks, and then what you're trying to map to is this diagram, right? You care about this guy. Now the point is that there's actually the Mobius transform. What it does is it takes the outer disk to the outer disk. That's fine. Now all of the other disks inside do not become disks, but they become ellipses. Because as they sort of become a little bit more and more distorted around. So what you do is the Mobius transform fixes the outer disk to the outer disk, but it also has the question about where the center goes. Now the center is going to go somewhere in here. You choose it in there. And then this disk becomes some sort of ellipse inside here. This disk becomes some other concentric ellipse that goes around it, but as you increase the radius of this, at some point it touches this origin without actually reaching this boundary, because it diffuses slowly. I mean, there's a sort of potential that prevents it from getting to the boundary, and that's the Mobius transform that you choose. You choose something that at the only choice is where the origin goes. in the Mobius transform, and you send it to some point inside the original circle that you have that it's small. And then how small does this disk need to be? It needs to be small enough that it fits inside the other one, even though it's now an ellipse. And how large does this need to be? It needs to be exactly whatever it is so that this ellipsoid, as you deform it, hits the origin. So there's an explicit calculation you can do because a Mobius transform is a simple function to write down, which you would just plug in and figure out what the value should be for that. But that's the way that when I had this growth property, it would actually imply a growth property that I've already ruled out. Because if I had a polynomial that violated this constraint, then it would actually, by undoing the Mobius transform and doing the inverse Mobius transform, it would actually give me not a polynomial, but some other holomorphic function, which would violate the Hadamard three-circle theorem. So that's a sense in which if I proved this for polynomials, it wouldn't actually suffice to do things there, which is kind of quirky too. So it's kind of exploiting and then there are these random walk interpretations of complex analysis too, where what's going on with the Mobius transform is, you have averaging statements for random walks that if, I take a point and I take the average around a boundary, I get back the value. But what you're really doing is you're deforming the random walk so that it creates a stranger average. And that's exactly what Mobius is doing, but beyond that, I don't know.
Other questions? Got chairs there. Yes, I have a quick question. So you mentioned you don't have a sense for what this perturbation looks like. Have you played with it numerically to see what comes out?
Yeah, so the thing is that you can write different LPs that are all polynomially equivalent. So instead of looking at the L0 norm of x times a minus e0, I could look at the L2 norm. And then I could change the other, infinity norm to an L2 norm, right? And then if you actually work with the L2 norms, the best x comes from a truncated singular value decomposition, because it turns out the best you can do is just remove things from the bottom up in a water-filling kind of way from the things that are small singular values. That was the thing that when I first saw robust local inverses seemed strange to me, was it seemed like, if all these questions are polynomially equivalent, why not just take the truncated singular value? What's bizarre about this is a bit technical, is that the family of matrices A that you get for different mu's actually commute with each other, so they can actually have a common diagonalization. So you understand exactly what their eigenvalues are, you understand exactly what their eigenvectors are. The point is that understanding the eigenvalues and the eigenvectors doesn't tell you anything about the singular values or the singular vectors. So when you take A, the gains from this all come from the fact that the SVD is much better to work with as a basis than the eigen decomposition. So when you actually take this matrix and look at its SVD, and you look at the small values, it's just impossible to figure out whether as you change mu, that's a polynomial relationship or an exponential relationship. So it's not even clear, forget what the singular vectors look like. It's not even clear what the relationship you need there to be true is true just numerically.
Mm-hmm. Yeah. Okay. Thanks. Other questions? Okay. Let's thank Ankur again.